All right, this is problem 3-90. It's on page 157. I'll read it. Determine the specific volume of superheated water vapor at 3.5 megapascals, 450 degrees Celsius based on A, the ideal gas equation, B, generalized compressibility chart, and C, the steam tables. Determine the error involved in the first two cases. Okay, so problem 3-90. We've been given that we've got superheated water vapor. The pressure is 3.5 megapascals. The temperature is 450 degrees Celsius. And we're supposed to figure out the specific volume, first of all, based on the ideal gas law. So the ideal gas law would say V, let's see, P is here, so RT over P. Now understand that this is the ideal specific volume. So we need the gas constant for water. Let's go look it up in the appendix. It looks like the gas constant for water is 0.4615. Everybody see that?
You got that from that front table?
First table, page 908. 4615 kilojoules per kilogram per Kelvin. Kilojoules per kilogram per Kelvin. And then the temperature is 450 C. Well, we can't use that, right? We have to add 273 to it. So that would be, that doesn't go over. That would be 6, no. I was thinking of 27. It's 73. So that would roll over to 7. 73 would be what, 23? Did we get that right? Yeah. Trying to work too quick. Okay, so 723 Kelvin. Where I'm off the video, I hope I'm not off already. The pressure was 3.5 megapascals, but to make my life easy, I'm going to convert that to kilopascals right off, because then I know the kilojoules unit will work out. And I'll have reasonable specific volume units. It'll be cubic meters per kilogram. Okay? So plug the numbers in your calculator and see what you get, please. So that's about half, 300. It's going to be about 0.1 or so.
0.095.
0.95. Okay, and the units would be cubic meters per kilogram. So there's the specific volume. Now they want us to compare this to the actual value by calculating a percent error. So let's just go back and look up the specific volume of water from the steam tables. This is really part C, but we'll just jump ahead and do it so we can calculate the percent error now. And all we have to do is look up 3.5 megapascals, which is on page 919. And 450 C. So 450 C, 3.5 megapascals. Looks like the specific volume is 0.09198. We'll write it down here.
$919,450.
Yeah, did I get that wrong? Page 919, 450 degrees Celsius.
Goes from 400 to 500.
No, I see a 450 in there. The lower right-hand table. Yeah, 4 to 450, 3.5 megapascals.
Oh, okay.
Did you find it?
Yeah.
Okay. So 0.09198. Yeah, I copied it down wrong. Okay. Or right. So cubic meters per kilogram. That's the actual number. You can see that the ideal gas law is really not that far off. But let's calculate the percent error. So the percent error would be equal to the actual value, 0.09198, less the ideal, 0.095, divided by, of course we need the absolute value, divided by the real, 0.9198. So throw that in your calculator, please. Let's see what we get for percent error. This will be decimal. We have to multiply by 100% to get it. Did you get 3.2%? Yes. Okay. Anyone second that?
Yeah.
Sounds reasonable. So the ideal gas law is actually doing a pretty good job. Let's see how close compressibility can get. Okay. I'll have to work here. Okay, the idea behind the compressibility factor is if we had a value Z, we could correct the ideal gas law, right? Notice that this is just the ideal specific volume, right? And so when we calculate the percent error, well, we'll just go do it. We'll go through the whole thing. So, what's up?
What is Z?
Z is the compressibility factor. Okay, so we have to get the compressibility factor from the chart. In order to get it, what we'll have to do is calculate the reduced pressure, which would be the total pressure, 3.5 megapascals, divided by the critical pressure. So we'll have to go back to the table where we found the gas constant. So page 908 again. Look up the critical pressure of water. Looks like it's 22.06 megapascals. Everybody see that? On page 908. So look up the critical pressure of water. It's next from the bottom, on the right-hand side of the page. Everybody see where I got the 22.06 from? Now, you already see that this is a fairly low pressure by comparison to the critical pressure, right? So we expect ideal gas behavior. So throw that in your calculator. What do you have? 0.159.
Yep.
Thank you. Let's do the same thing with the reduced temperature. So the reduced temperature, now be careful, you can't plug in 450 here. You have to have the absolute temperature. We have to plug in 723 Kelvin divided by the critical temperature. Anyone see the critical temperature for water?
647.4.
Good. 647.1 Kelvin. This looked a little bit concerning because the critical or the reduced temperature is close to 1. In other words, the critical temperature is close to the actual temperature. Okay, so that ratio is what? It's 1 point something. 1.7? 117, thank you. Notice both of these are non-dimensional. Okay? Now what do we do with this? Well, we go back to the compressibility chart, page 932, and we try to read off the graph. Now notice that the reduced pressure is pretty low, so we want to be on the upper chart. Okay? Not the lower chart, because the lower chart is not zoomed in on the area we want, so we won't be able to read it off as accurate. Okay. So 0.16 or so. There's 10 division lines, so 0.11, 2, 3, 4, 5, 6. I would choose one where the we've got to go up above, right through the chart, or the insert in the chart. Okay, so 0.16, let's see, and reduced temperature of 1.1 some odd. Let's see, I see a reduced temperature of 1.0, 1.05, 1.1. We're closest to 1.1. Everyone see the line for reduced temperature of 1.1? Make sure, I'll just pass it back. So reduced temperature 1.1 is here. I'll just reduced temperatures. 1.1 is right there. So just turn around and pass it back, if you would.
Yeah,
Sure you see it. You see it?
sounds good.
So just turn around and pass it back. Make sure they see it.
So actually,
You guys see where it's at?
yeah.
Make sure you pass it back, and second row, pass it back to the third row once you know where it's at, to make sure everybody's with us. So what compressibility factor do you read off? I'm trying to read it as well.
0.94.
Yeah, we said 0.95.
Yeah, something like that.
Ballpark.
Yeah, that looks reasonable, 0.94, 0.95. Everyone agree with that? And it makes sense that the compressibility factor should come out. What do you guys think, 94 or 95? 95, there it is. Okay, it makes sense it should come out high because we expect that, right? We expect fairly ideal behavior. So this would be 95% of essentially the ideal specific volume we had, 0.095 cubic meters per kilogram. Okay, let's just finish it off really quick for the sake of the video. So multiply that out if you would, please. So 95% of 0.095 is how much? .09025. And then the percent error is just 0.09198 less 0.09025 absolute value divided by 09198. So what do we get for percent error?
A 0 point, not 10.
Yeah, 0.09198 less 0.09025 over 0.09198. Should be a pretty small number. Of course, then you're going to multiply by 100%.
0.18119.
How much? Point how much?
1.88%.
1.88%. Everybody agree with that? Now, if we had read the compressibility factor off a little more accurately, it would probably be even closer. But it's a small percent error. All right, thank you guys for your patience. And don't forget there's a quiz due Monday.